e seguiremos com o evento. Professor Reza.
Tudo bem? Boa tarde, pessoal. Good afternoon. I would like to invite Professor Stefan Maier for his presentation. Stefan, can you hear me, please?
Yes, hello. Good afternoon.
Hello, how are you?
Nice to meet you and see you. Yeah,
Nice
fine.
Okay, before we start, I would like to present you to our public, give you a little bit of your great CV here. And Professor Stefan Maier, he's been graduated in physics from Technical University of Munich in 1999, master in applied physics in 2000, and doctorate in applied physics in 2003 from California Institute of Technology, Caltech. He did postdoctoral work at Caltech since 2003 to 2004, and he was a visiting professor at Singapore in 2009 and in Universidad de Buenos Aires from 2013 and 2014. He is currently a professor at Ludwig Maximilian University of Munich since 2017 and Imperial College London since 2007. He was awarded several awards, including the Sackler Prize in the Physical Science from Tel Aviv University, Fellow of the Institute of Physics, Patterson Medal of the Institute of Physics, Fellow of the Optical Society of America, and Royal Society Wolfson Research Merit Award. He is author of over 300 articles, in addition to the great book entitled Plasmonics, Fundamentals and Applications. He works in the field of physics with an emphasis on fundamental and applied plasmonics, nanophotonics, and metamaterials. Professor Stefan Maier, it's a great pleasure for us to have you here in our workshop, and thank you very much to accept our invitation. I would like to remind you that you have 55 minutes to your talk, and we have 5 minutes for the questions and at the end of your talk. And you will be notified since once 5 minutes left to the end of your presentation.
Perfect.
You may start, please.
Okay, so thank you very much to you and all the organizers. It's my great pleasure to be there. Would have been nice to come in person, but maybe sometime in the future years to come. So let me share my screen and let's hope we get this to work. So you should see my first slide now here in full screen, I hope.
Yes.
Let me just arrange my video bar so I also see some of you as I talk. I'm not just talking into a black box as we have done all now for already way too many months. Okay, so I see there's a large number of participants here. So like I hope most of you are students, postdocs that are interested in optics, in nanophotonics, nanoscience, in general interaction between light and matter. So I'm going to try to tell you a little bit more now about that field and in particular what we have done in it over the last couple of years. So maybe first a tiny bit of background to us. So at the moment we are located here in the city of Munich, right next to a park. So very nice location. And this institute that you see here in the center of Munich, that's the so-called Nano Institute Munich, and we occupy about half of it. So we are a group at the moment of about 45 people, physicists, people from material science, lots of chemists, even 2 people from electrical engineering. So it's a really highly interdisciplinary group, and that's something that also I find very exciting about the research field that we are in, about this research field of nanophotonics that I will strive to tell you a little bit about now. It combines a very large area of skills. So I will give this talk now, obviously, but the work is really due to all of the great people in my group that have contributed to this work. And I'm just pointing out here a couple of faces. So these 19 people, they're all professors now, you see, all over the world. So they've gone through my group over the last 12, 13 years. And these are really the ones that I'm most proud of. And they are what drive me on in in science. Yeah, and I think if you want to start a career in science, yeah, you should always think of yourself and like the generation after you, you know, that will bring out the new discovery and progress to come. Yeah, and you see, for example, we have also one alumni now. It's actually this guy just here. That's Gustavo Greenblatt, who is now a professor. Well, not really close to you, but on like a global scale, relatively close to you. So he's now a professor at the Universidad de Buenos Aires. So what are we working on? So we are working on how we can control the interaction between light and matter by nanostructuring materials. So we use mainly processes that get used in semiconductor manufacturing. So top-down lithographic processes to pattern either dielectrics or to pattern metals into structure sizes that are smaller than the wavelength of interest. Okay, so if we are speaking about visible light, our typical structure sizes for the units that we operate with are on the order of like 100 nanometers or less. Yeah, and we use as materials either dielectric materials, I will not talk a lot about that today, or metallic materials where you can excite so-called plasmon modes, like a large part of my lecture will center with that, in order to generate tightly confined fields of light on the nanoscale. And it's then really these tightly confined fields of light that enable us then to have a new paradigm for the control of light and matter interaction. So a lot of the work that we do can, I think, on the fundamental scale, be kind of like summarized via these 4 different topics. Yeah, so we want to nanostructure matter to enhance light-matter interaction, and for example, to get control over the emission of light. We want to use highly confined so-called hotspots of light for enhancing the interactions with molecules in the context of surface-enhanced sensing and spectroscopy. I will also show how you can do chemistry on the nanoscale with such hotspots of light. And what I will not talk about today is how you can then also combine such hotspots with 2-dimensional materials to strongly couple light or to effectively couple light into atom sheet layers of materials. So this is really the fundamental work that our group is known for, and which we have started really when we got established at Imperial College at around 2008. But then in more recent years, so really in the last couple of years, we have also made, together with a great set of collaborators, strives into more applied work. And in the last few minutes of my talk, if I have time, I will show you a little bit of the applied work that we do, and mainly in the context of using nanostructured surfaces, so-called metasurfaces, for new forms of video holography, which you might find quite exciting. Yeah. Other applied work that we do at the moment is we put such metasurfaces, for example, on optical fibers to make new fiber optical instruments, mainly for imaging, or to find new ways of harvesting light into very thin layers, or guiding light in basically almost air waveguides. Yeah, but I can't cover everything, but I also want to give you a little bit kind of an overview of the breadth of research that there is out there, and particularly that we are doing, obviously, in nanophotonics. Yeah, if you see anything else there that interests you that I can't cover today, please just feel free to email me. I always try to answer emails relatively quickly. So now, but let's start with a little bit of introduction, and I want to start very basic by considering something that you all know, and this is one of the basic problems about how we can manipulate light when we go to small length scales. And I want to start with this beautiful image here that we see on the right. So some of you might be interested in photography and the history of photography. So you might have heard of this lady here that we see to the left. Her name was Berenice Abbott, a very famous photographer, mainly for her work in New York City in the 1920s and 1930s. I think what we see here on the right, and this beautiful rays of light here coming through these windows, is Grand Central Station in New York City. So what she has also done, actually, is she has made some beautiful photography for a physics textbook. So for textbooks that got published in the late 50s and early 60s. And I just want to show you 2 of these here. You can see the originals in Boston and in like New York, the original prints, and it's these two, and they deal with wave phenomena, right? And they are like a good reminder for us that if we are in the far field, so if we are on macroscopic length scales that are larger than the wavelength or significantly larger than the wavelength, right, then we all know how to control light. Yeah, if you look at this prism here, right, we know that at an interface between two materials, we have refraction and reflection, and this way we can guide light and we can store light on a length scale that is on the wavelength or larger. Yeah, I mean, like you can even explain rudimentarily, for example, for how an optical fiber works, right? That usually has a core diameter on the order of the wavelength in the material by just thinking about total internal reflection, right? So the ray picture of light. But you also all know from your very elementary optics classes, right, or like a wave class in general, that of course once we reach the wavelength scale and once we want to control a wave phenomena on a scale on the size of the wavelength or smaller, then it gets much more difficult, right? Because now interference and diffraction sets in. Yeah, obviously. Berenice Everett couldn't take a nice photograph of that because you have exactly these problems, right, of interference and diffraction. But if you look at the one here on the right, it like shows the problem. So these are like water waves, right? It's a beautiful picture of water waves that get generated via these two like tapping devices on a small sea of water, right? And we see here these planar spherical waves propagating, and then you can see the interference pattern, right? And this is our reminder that if we go to the near field, light is suddenly much harder to control. So now what like can we do if we now want to confine light onto small length scales, right? And like the obvious reasons why one would want to do that is this way you can make your optical devices smaller, you can make them lighter, you can make them less material intensive, right? The more light we can, for example, focus into a thin layer of silicon or a 3,5 material, right? The thinner we can make a solar cell, the lighter we can make a solar cell, the less material do we need. So if you think just simply about sustainability, about energy balance, right? So like less is more, yeah? And we all know that, for example, also from our computer chips, our computers and laptops, right? Like lot of the speed increase, or like basically all of the speed increase these days in electronic components is given by the amount of cores that we can package into a very, very small space. So like by the reduction in the size of the transistor, right? Now, obviously there are like limits to that, but typical length scales there for electronic components, if like we think about gates in modern field effect transistors, are a couple of nanometers. Now, clearly that is not possible if we want to think about light, right? Let's think about a transistor, for example, operating with light precisely because we have this limit of diffraction here, right? That's, as you also know, is roughly on the order of half the wavelength of the material. So what are ways that we can confine light into smaller length scales? So what I've put on this slide is basically two, well, even though you see like three different ways here, actually two are very similar. So like, let's start maybe first with like the brute force one, which I will not talk about. This is the one that you see in the middle here. This is, you make a resonator out of a high index dielectric. This way, you, of course, you still have the diffraction limit of light. Yeah, so if you would make, for example, two little pillars, as you see here in this SEM image, this is a material called gallium phosphide. It's a 3,5 material. You can excite dipolar resonator modes. So like think of it just as like a small mirror cavity here, the left one, a small mirror cavity here, the right one. And of course, physically, you can confine the light here to a nanometric scale. Yeah, because of course the wavelength, as you all know, the wavelength of light in the material is reduced, right? So if this material, gallium phosphide, if I tell you this has a refractive index of 3.5, that means that the wavelength of light is reduced by a factor of 3.5 in that material, right? You all know that from like Snell's law, meaning that the diffraction limit, so the limit of basically these interference fringes, if you wish, in that material is now the free space wavelength divided by 3.5, roughly. Yeah, this is all very like hand wavy here because we are just interested in orders of magnitude. So you can't beat the diffraction limit this way, but you can still get to very small distances for spots of light. And if you then, for like example, make a small cut, yeah, into such a gallium phosphide resonator so that you have two of these, then you can still get a very high field enhancement in there that you can then use, for example, for the Purcell effect to enhance the spontaneous emission rate of a small E emitter that you put in there. But there's also a way actually to really beat the diffraction limit. And that is if you couple your light excitation. So if you couple the electromagnetic field of light to a matter excitation. And why do you need to do that? So you, if you think about wave optics and about like radiating waves, right? You all know that light as an electromagnetic wave is, if you wish, again, if we talk about it hand wavily, a continuation of electric and magnetic fields, right? If you think about the third and fourth Maxwell equation, you have a fluctuating electric field that generates a magnetic field, that generates an electric field, and so on and so forth. And this way you get a radiating wave. And that is possible because you have an equipartition between the energies in the electric field and in the magnetic field. And energy in the far field is constantly able to fluctuate, so to speak, between the electric part and between the magnetic part. But now the issue is that if you go now to the nanoscale, then the magnetic fields are vastly reduced in strength compared to the electric fields, and you are not able to continuously move from electric part of your EM wave to magnetic part. Yeah, the only way that energy can be conserved, and you can rigorously show that, is by the cavity to radiate. And this is a way, for example, to derive the limit of diffraction. So like what you need to do is you like need to find another energy storage, so to speak, in which the electric energy on the nanoscale, yeah, can temporarily move before moving all back into electric energy. And that is a matter excitation. So what you do is you couple the electromagnetic field either to the motion of an electron cloud to a plasma in a metal, then you have a so-called plasmon polariton, as we see as an example on the left here. And this has spurred around 20, 25 years ago, a field that is now known as plasmonics. Or, and that's something I will not talk about, but it's very similar, and you see it here on the right, you can couple the electric field to a phonon mode in a polar dielectric in the mid-infrared. And the mathematics of these so-called phonon polaritons and plasmon polaritons is very, very similar. But I will deal with plasmon polaritons. And these enable you now to truly confine light to below the diffraction limit. So what we see here in this image, and I will tell you later very briefly how like this was made, these are two small triangles of silver. And this is a so-called bow tie nano antenna, since it looks kind of like a bow tie. Yeah? And what you see here is, first of all, a like length scale. So you see this gap size here is maybe a couple of nanometers. So these two silver triangles are very close to each other. And like what you see here now is a well-defined optical mode that corresponds to a free space wavelength of about 550 nanometers. Yeah. So you see that its energy, at least like visually, yeah, is confined into an area that's much, much smaller than half of that. Yeah, even much, much smaller than half of that would be in silver itself. Yeah, so you have here a so-called hotspot of light, and hence also this name that I just said. One can call this a nano antenna because what it enables us to do is that at this particular frequency, it enables us to collect light into an area that is way below the diffraction limit of light. Yeah. So you have very high localization with this. This is all great, but it comes as a price. And the price is that you also have fields in the metal itself. And these fields can then be absorbed, right? Because the electric field couples to the motion of electrons, yeah, to basically a motion of a whole electron cloud in this metal. And as you all know, even like if you just think about ohmic damping, right, that has a certain decay or dephasing time associated with it. So the more we confine, yeah, the less actually this excitation lives. And I will show you later that this excitation actually only lives for a couple of femtoseconds, yeah, which is a problem sometimes, for example, if you want to guide energy, but also has some intriguing opportunities then actually to use such fast processes. Okay, so let me go back to my slides. So like what I want to discuss now in the main part of my talk, and depending on how we go, so probably for at least 40-45 minutes or so, is this the opportunities that we have with such plasmonic modes for the localization or for the harvesting of energy, and then also for converting that energy into other forms of energy. So from the photon field, for example, I will show how we can convert into coherent mechanical oscillations, and also how we can can trigger chemical transformations of molecules that we might want to put close to our metal nanoparticles. And then in the very last few minutes, I want to show you a little bit of work that we do in holography based on nanophotonic structures. Yeah. I should also say, if like one of you has like a really burning questions, so I don't know how you handled it previously, but I would be also happy if you would just interrupt me. Otherwise, we can do all of the questions, of course, at the end. Okay, so now a few more words on plasmonics and how these plasma modes come about. So like what you see here is one of the earliest applications of these modes. So like this is a glass cup that some of you that have maybe seen a presentation of plasmonics have probably seen, because you can see this in many presentations about that field. This is a cup that one can also still see in 3D, so to speak, in the British Museum in London. It's from the late Roman Empire, I think about third century after Christ, and it looks in reflected light green and in transmitted light red. Okay, and this peculiar behavior comes about because this glass cup is doped with small metallic gold-silver alloy nanoparticles that have their plasmon resonance. So they are resonance where they have the strong interaction with the light field in the green part of the spectrum. Yeah. So if you shine light at it and you look at the reflected light, green light gets preferentially reflected. If you put a candle into it and you look at white light coming through it, green light gets preferentially absorbed and scattered outside the line of sight. So it looks red. And the basic physics here we can understand just from classical electrodynamics. It is simply that we have an electromagnetic waves that drives the plasma cloud, so the free electron cloud, in a small metal nanoparticle coherently back and forth. Yeah, so we don't need quantum mechanics unless we come to particle sizes that are very small. Very small means on the order of a couple of nanometers. Yeah, but for this strong interaction with light, we need to have a substantial amount of volume of our particles. So typical particle sizes here in plasmonics are on the order of a couple of tens of nanometers. Yeah, so usually you are below 100 nanometers, so well below the free space wavelength of light. But we can think about it classically simply now because we have so many electrons available now in our free electron cloud that at room temperature, yeah, so we have so many energy levels compared to kVt at room temperature that everything is smeared out. We can think about it as a continuum problem, or like in other words, simply as a mass on a spring. Yeah, and just as with a mass on a spring, classically, right, a classical harmonic dipole oscillator for a certain frequency, now a resonance can arise. The amplitude of our excitation gets larger, so to speak, and that is now exactly this plasmon resonance that then leads for a specific frequency, and that frequency depends on the shape of the particle, whether it is a sphere or whether it is a cube. It depends a bit also on the size of our particle, and it depends on the material that the particle is made of. So it needs to be a conductive material, a metal. Usually you use gold, silver, or copper, because they show the least amount of damping for visible light, and it then also depends on the refractive index of your dielectric medium around it. And then when you then have this resonant amplification of this motion, right, you like all know that a moving charge cloud radiates, right? So if you now have a resonant amplification at a particular wavelength, at a particular color, yeah, at a particular frequency, then that leads then to this resonantly enhanced scattering of light that we see here in the green light, and then also to the resonantly enhanced absorption of light. But crucially, what we have in addition, and that's what I showed with my image that is here of this bow tie antenna that you see again here on the right, what you have in addition, and that is now really where the power of plasmonics really lies, is you have a vastly enhanced local electric field close to the surface of the particle. And that is because at that resonance frequency, the particle basically looks for light at that of that particular color, of that particular frequency now bigger than it really is. So it kind of acts as an antenna that almost, almost like the antenna in your like cell phone. It like filters for a particular frequency and can be much smaller than the wavelength, than the free space wavelength corresponding to that frequency due to this resonant E effect. And it's really this resonantly enhanced field now that you exploit in plasmonics. And then you can enhance light matter interactions if you are then able to place, for example, molecules into this enhanced fields. Yeah. So we cannot see these enhanced fields with the microscope simply because our optical microscopes are diffraction limited, right? They operate, if you wish, with far field optical elements, right? Lenses and mirrors, but you can see them, for example, if you excite these plasmons, not with a plane wave, but if you excite them via fields around an electron beam. So if you make a plasmonic structure, let's look again here on the right at our little triangles, with this little gap, and you put them now in a transmission electron microscope and you raster scan your beam over it, then of course you like get an image, as you see here, like a very nicely resolved image, right? Electron wavelengths are very, very small. So the diffraction limit is very, very small. But also an electron is a moving charge, right? So an electron beam now has also an electromagnetic wave associated with it. And it's the electric and magnetic fields. Well, it's the electric fields surrounding this electron beam that can now also polarize this particle and also, just like a plane wave, now set the electron cloud into motion. Not in a motion just of one mode, since it's not a plane wave, but in a superposition of their eigenmodes. So depending on where I now put my beam can excite a different linear superposition of electron cloud motions in this particle, okay? And like, how can I see that? I can see that if I now put an electron detector and like energy detector on the other side of my very thin sample. Yeah, this is a transmission electron microscope. So I need to be able to fabricate these antennas on a substrate that's, let's say, only 20, 30 nanometers thick. But then if now my beam goes through it and it has excited some of these plasma modes, the beam will have lost energy. So if I now have an energy dispersive detector on the other side, I can take an energy spectrum, such as we see here below, this red curve and this blue curve. These peaks show where my electron beam has lost energy. Yeah? And the red curve corresponds, for example, when I put the beam here in the middle, the blue curve when I put the beam here on the side. And these are now the different plasma modes, the lowest order plasma modes that I have excited in the system here. And now I can put an energy filter around this peak and raster scan again over it. And this way I can make these beautiful images that you see here on the right of what the field profile of these modes looks like. Yeah, so these are the three lowest order modes. One is a symmetric dipolar mode, an asymmetric dipolar mode, and a quadrupolar mode. And I'm only showing this so that you can see, first of all, that you can appreciate how closely the fields are confined. And secondly, also like the beautiful symmetry, right? So you see here the lowest order modes, a field enhancement in the middle here and on the sides. The next one, the field is mainly enhanced at the like edges and again in the middle. And on the third one, it's mainly, sorry, here it's mainly in the at the corners, and here on the third one, it's on the side, right? Here, like on the like side edges. Yeah, and like this is really one of the powers of this field of plasmonics. So if you first kind of get like introduced to this field, you will see that one of the biggest applications is now to utilize these hotspots of fields to enhance the interaction with matter from a viewpoint of sensing. Yeah. So for example, you can make quite complex antenna structures that have multiple resonances, and then you can use them, for example, for the enhancement of fluorescence. So if you now put a fluorophore close to such a metal structure, yeah, you will see that you get enhanced fluorescence close to these resonators. You can use them to enhance Raman scattering, and that's So this is so-called SEIRs, surface enhanced Raman scattering, and like that's where the real power actually lies, because SEIRs, for example, scales with the fourth power of the local field. So if I tell you that in the best plasmonic structures, you can get a field enhancement on the order of, let's say, 1,000, then you would get a SEIRs enhancement 1,000 to the power of 4. Yeah, so a vast amount of the plasmonic literature, yeah, you will find countless papers where they exploit such structures for surface enhanced Raman scattering. But if you're able to push a resonance, and there are tricks also in the mid-infrared, then you can, for example, also enhance the absorption of infrared photons. So you can do something called SEIR, which is called surface enhanced infrared absorption. Yeah, so this is still up to this point one of the most prominent applications, in a sense, almost like a straightforward application of plasmonics. Yeah, you make small hotspots of light around your metallic nanostructures, you bring a material in it, and you enhance the light matter interaction. Yeah, and like mainly a photon interaction, if you wish. Yeah, you can also use them for example for the enhancement of second harmonic generation. Okay, so now I will actually probably skip this part here because I want to make sure that I have enough time. I took a little bit longer for my introduction to show you now how you can think about using such metallic nanostructures also to convert energy. Okay, and like what I like mean by that is that so far the way that I have explained plasmonics is we make small hotspots of light. You can then put a material into it, and you enhance a photon interaction with that material, right? So I've briefly told you about fluorescence, surface enhanced Raman scattering, surface infrared absorption. Another very prominent part, yeah, is also excitation of higher harmonics. Yeah, so there's like a large amount of literature where the high fields around such metallic nanostructures get used to enhance the effective either second order or third order susceptibility of a material that you put into such a hotspot. Yeah, so like in a sense, these field hotspots can aid the conversion of photons from one frequency into another. What I want to show you now, though, is how we can also utilize these plasmon excitations to convert energy from a photon, so from the electromagnetic field, to other forms of energy. And in particular, I will show you how we can excite coherent vibrations in such coherent mechanical vibrations in such metal nanoparticles via light when we excite them or probe them at their plasmon resonance, and how we can then use that to launch mechanical waves, for example, propagating on the substrate. And then I will also show you how we can use it actually to trigger chemical reactions close to the metal surface. And these energy conversion processes are gaining more and more attention in the field of nanophotonics and of plasmonics, since they also enable us to look at a wider variety of plasmonic materials, not just gold, silver, and copper, but also materials that are actually higher absorbing. So we don't see absorption as something relatively bad that has hindered progress in plasmonics, but we see it now actually as an advantage. And why do we see it an advantage? Because for energy conversion from the photon field into either a mechanical oscillation or into a chemical transformation, which is a charge transfer, the plasmon actually needs to decay. Yeah, so we are now not so much focused anymore on this field hotspot that I've kind of tried to describe in my introduction, but we are now actually more focused on the other part of the plasmon, the motion of the electron cloud. Okay, and we will look at what happens when the motion of this electron cloud now actually decays, and this way directly excites meta excitation in that particle. So in this field of energy conversion, this is a really good review article here. Now it's like more from a viewpoint for chemistry, but if you're interested in that, I really encourage you to like read this. So it's by David Way from Gainesville in Florida, who has really nicely like summarized, and I particularly like like this plot here that shows the different time scales that are involved into such energy conversion processes. Okay, and like what like basically happens is you have your plasmon cloud. Your plasma cloud moves back and forth, right? That is your localized surface plasmon that you have in your particle. But then after a few femtoseconds, the plasmon decays, and it decays, I will show that in an animation just in a moment, into a single electron hole pair. And then this electron hole pair has a lot of energy. And then if I'm able now to harvest either the electron or the hole of this electron hole pair, then I can use this energy for something else, for example, for triggering a chemical transformation. Yeah. So if there are any kind of chemists here in the audience, look at this article here. It like discusses how you can use plasmon decay and the energetic charge carriers associated with the decay of plasmon for molecular transformations. So what I will show now basically, and like discuss a little bit, is how we can think of a small metal nanoparticle now not only as a way of generating a small hotspot of light, yeah, but also due to the decay of the plasmon, thinking about it as a means to locally increase the temperature, and associated with that, right? So like temperature, heat, that's a random, highly disorganized motion, right, of my atoms. But parts of that energy is also steered into actually an ordered displacement of my metal nanoparticle as a whole. So basically, when my plasmon decays into a first hot electron hole pair, then this hot electron hole pair, via electron-electron collisions, and then also via thermalization with the lattice of atoms that make up this small metal nanoparticle, actually sets this metal nanoparticle into a vibrational motion itself. Yeah, so I basically have now a small mechanical nano oscillator that I can selectively excite now by a light. And this is something that we have had a lot of fun with over like the last couple of years, mainly in a collaboration with a group of Andrea Bragas in Buenos Aires. So you mentioned in the introduction that I spent some time there. So like that's where the work that I will show you now originated. Yeah, there are also two really nice review articles on this, on how you can use light to coherently excite by vibrational mechanical motions in metal nanoparticles, and it's well, it's like these two articles here. Yeah, I should like also say, if you are interested in this talk, I am happy if you email me. I can give you a like PDF of this, and then you have then you can just click on these. I will not do it now because it's going to open the like web browser, and then you can read these nice articles here. And one of the intriguing parts here is that the mechanical eigenmotions of such small metal nanostructures are at gigahertz frequencies. So they are very, very fast. Yeah, these are some of the most fastest mechanical oscillations on record. So now let me now like show you how this works. Okay, so and like how you can actually detect this. So you take a small metal nanoparticle and you excite it, yeah, with an ultra-fast laser beam. And you can do this excitation. For example, here we like did it at the plasmon resonance itself. So it interacts strongly with the beam of light. It generates these like hotspots, and then the plasmon starts to decay, and parts of that energy now goes into vibrational motion of this particle, as we see in this simulation down here. So this is a simulation done with a partial differential equation solver called COMSOL, and it solves the Navier equations of continuum mechanics if we excite this little piece of metal here with basically a thermal shock. Okay, and you see here an oscillation, and the oscillation amplitude is really small. It's a couple of picometers in its longitudinal eigenmode. Yeah, but now like think about it. So now the like particle actually, it like moves a little bit, but this movement now actually modulates the plasmon resonance itself, right? So like I have told you before that the frequency, the color at which a particle strongly interacts with light, right? Think back to the color of this glass cup that I just showed you. It depends on the shape and size of the particle. So if the particle now oscillates at a particular frequencies back and forth, I should see a modulation of the plasmon frequency exactly at this mechanical frequency. So if I now do pump probe spectroscopy, meaning I not only come in with a pump pulse, but I then also come in with a probe pulse and I have a DLA line, and I look at the differential transmission or the differential reflection of my probe signal, and I then Fourier transform it, I should get out these mechanical frequencies. And indeed, that works. So like in this work here, what we have then explored is, can we actually modulate the strength of these mechanical oscillation if via brute force, secondly a lithography step, we tie parts of this metal nanoparticle more strongly to the surface. So if you look at these SEM images here on the left, what you see here are here on the very left, the bare metal nanoparticle, and then one where we have put a thin glass bridge right in the middle. And here one next, the green one, we have put two thin glass bridges right at the end. And then we've made one where we encapsulate the whole thing in glass. And this way we wanted to see, can we change the relative strength, for example, of the two lowest order mechanical modes that such a particle has. So what we see here on the left, this is the mode that we've just seen. This is a longitudinal mode, and the mode here on the second left, this is a breathing mode. Okay, so the particle expands also a little bit in the other dimension, right? And the idea is now, and you can kind of see that here in these simulations, if you have a glass bridge right in the middle here, let's look on the very left. Yeah, you see the breathing mode doesn't really affect the glass bridge, meaning that if you put a glass bridge on it, the strength of the breathing mode shouldn't be affected very much. Whereas, sorry, the strength of this longitudinal mode shouldn't be affected very much. Whereas the breathing mode that we see where my mouse is now, here the glass bridge moves a lot. So we should be able to change the strength of this mode quite a lot. Conversely, if we put the two bridges at the end, so now we have the second to the right, you see now it will be the longitudinal mode that moves the glass bridges a lot. Yeah, well, and the breathing mode, you see maybe a little bit less, but also a bit. So if we then do that experiment and we look at the relative strengths between these two modes, so one mode is just below 10 gigahertz, the other one is around 16, 17 gigahertz, we can see that we can change the relative strength of these modes. Yeah, but this was really just kind of a warm-up study for us together with Andrea. So I should also say these experiments got actually performed in Buenos Aires. This is really just a warm-up study, because what we really wanted to see as well, what can we do with this, right? So you might ask, okay, that looks all very neat. It's maybe quite nice fundamental physics, but what can you do with it? Well, one thing that you can do is that you can use this now, of course, as a nanometrological tool to learn about the elastic properties of the material around your metal nano oscillator. Yeah? So if you, for example, again, take a small gold particle, okay, and you look at the frequency of its mechanical eigenmodes. Let's again maybe just think about that mode where the whole particle kind of moves nicely back and forth, like the longitudinal mode. So you do pump probe, you take a transmission spectrum, you take a Fourier transform of the oscillation that you see, and you get your gigahertz frequency. If you now coat the particle, yeah, now let's say not with a glass bridge, but just with a polymer, yeah, that will shift this mechanical frequency. And if you then now correlate this with simulations of the Navier equation of that, you can then, for example, find out about the Young's modulus, so about the elastic properties of your coating material. Yeah, so you can use this now to basically, on the nanometer scale, on the length scale of this metal nanoparticle, find out what are the elastic properties. In this case, in this simple study here that you can see in this paper here, we just used PMMA. Yeah, so I will not go into the details here. You can see it all in this paper. But then you can, for example, now use this to locally look at a change in the elastic properties that are induced by heat. right? So here we use pump probe, as I've said, to set the particle into motion and then to actually re-accord this oscillating time trace. But if we crank up the power of our probe beam E enough, we can, for example, move the PMMA via a phase transition from a rubbery state into a glassy state. And then you can directly read out the hysteresis of this process, for example, by looking at the shift in this, in this frequency peak here from blue to a red, yeah. Or like you can also just like put it on like a temperature stage. You like leave your like laser power quite like small, and then you see here the two hysteresis curves. So this would be one probably quite straightforward application of this energy conversion. But what's probably even more like interesting is the like following that I'm again showing you here by like a full field simulation of the Navier E equations. And like that is, since your particle is on like a substrate, if you just look on the left here, yeah, the like motion of this particle that we can excite by a light will now in itself actually trigger a mechanical surface wave, a shear wave on that surface. So these little rings that you see here going out, yeah, these are now, these are not plasmons or anything. There's no like metal here. Yeah, this is in this case just a small gold bar on glass. These are mechanical surface waves that we have excited via putting this particle into vibrational motion. And then you could, for example, think now, well, can we now maybe use such a particle to excite locally a defect mode? So like this is something that we haven't done yet, but something that I would very much like to explore. So like, let's say we now take our glass surface and we now structure it via holes in order to make not a photonic crystal, which some of you might have heard of, but a so-called phononic crystal. So a crystal where we now have band gaps, yeah, for sound propagation. And if we then leave one of these holes out, yeah, then we can have a local phononic defect mode, which we could then excite, yeah, via such a small metal nanoparticle, for example. So here you see a full field simulation of this, where we excite a phononic defect mode just in this region of the defect here by setting this small particle into motion. And we have some good evidence that that this works, via like a work that we did about 2 years now, well, 3 years now, like already. And like this was actually spearheaded by a Brazilian student from Sao Paulo, Rodrigo Beate, that did his PhD with me under the, I think now unfortunately not so much operational now, but at that time great Science Without Borders program. Yeah, so he came to me at Imperial College and finished his PhD there, then moved to us with us to Munich as a postdoc, and he conceived this really nice scheme to find out if what we see here on the left actually works. So like he said, well, how can I find out whether a mechanical wave propagates away from my metal nanoparticle? And like he said, well, let's not take one particle, but let's take two. Okay. And whereas before, sorry, I will go back once more. Whereas before, we have always done pump probe spectroscopy on the same particle to study its motion. Let's now just do pump probe spectroscopy on two different particles. I pump one particle. If the particle now starts to vibrate, and if it, well, we know that it starts to vibrate, but if it then sets a mechanical wave into motion, when that wave now hits our second particle, it should now excite, not via light, but just via the mechanical wave itself, also a vibrational motion in this particle. So if I now probe on that particle while pumping always on the other one, yeah, I should also see a differential transmission or a differential reflection on this probe particle. And that really works. And like together with Andreas' group in Buenos Aires, Rodrigo nicely showed that. So you see here in SEM images, I don't have time to go into the details, but we basically have two particles. They are a couple of microns apart, because this is the typical decay distance of this mechanical surface wave, and we excite one particle and we probe on a particle farther away. Yeah, so we use the same pump probe setup, but we now separately, we spatially separate pump and probe pulse. You need to do like a lot of checks and balances that are all described in this paper here. So you need to find out first, what are the vibration eigenfrequencies of these two particles, why are pumping and probing on the same one as before, and so on and so forth. But then if you do the real experiment, so you pump on one and you probe on the other, you get traces such as this for the transmission through the probe particle. Yeah, so you see, depending on the like distance, so from blue we go from very small distance between the two to red to larger distance. You see at some point our receptor particle, the particle where we only probe, gets set into motion, and we see this differential transmission here. And now that is due to the fact that we have pumped our S particle. We have a mechanical wave going from S to R on our glass substrate. R gets set into motion. We get our differential transmission there. Okay, and then again, you can then use that now, for example, to find out about the like wave speed of this mechanical surface wave. And as you would expect, it's just a little bit below the speed of sound in bulk silica. This was a silica substrate, because that's what you would expect for this Rayleigh shear wave. Yeah, so like we are having now, also like in like Munich, like quite a lot of fun with trying to extend this technique. Okay, so now like lastly for this part on like energy conversion, I now want to show you what we can do if we kind of how like shall I put it, in a sense, if we don't wait until the decayed plasmon has given all that energy to the particle to make it vibrate, but like if we try to actually extract the energy from the electron hole pair that has been generated when the plasmon decays, before it has thermalized with the phonons and before it has set that particle into motion. So I want to explain this to you now like a little bit. The like opportunity here, I'm seeing I'm already quite advanced in the time in like my like talk, but I'm going to play you now like a nice little like animation that kind of like summarizes a bit what I've tried to explain so far about plasmon decay. So let me like play that now. So we are taking a metal nanoparticle, right? And let's again say what like a plasmon is. So we have light. The light sets the electron cloud into motion. I get my hotspots of field, okay? And then after a few femtoseconds, yeah, this plasmon will decay. And there are now basically two different decay processes there. Yeah, one leads to the enhanced scattering, one to the enhanced absorption. The enhanced scattering, think of the green color that we saw for our glass cup, is basically the plasmon decays back into a photon. Okay. But the more interesting part for us now for like energy conversion is the absorptive one. So the plasmon decays into an electron hole pair. And now this electron hole pair has a lot of energy. It then starts to lose its energy via electron collisions. And in the end, as we have just seen here, it sets the particle into motion itself. Okay, so these were the vibrational modes that we've just seen. But now, what happens now if we now put a molecule on the metal nanoparticle surface, and while the electron and the hole still has this excess energy from the decay of the plasmon, right? Because like think about energies for a moment, right? We are dealing with photons of visible light, right? So like a typical energy of, let's say, like 2 eV. When the plasmon decays, all of that energy gets given to a single electron hole pair. So if we are now able to harvest this energy by injecting one of these charge carriers into a molecule that we put on the surface, then we have a charge transfer to a molecule. So we have triggered locally a redox reaction. Okay. And this is where we can locally influence chemistry. And I want to show you now like a couple of examples of that. Yeah. So the idea is the electron here. Yeah. So before it has lost all of its energy, it like enters into an unoccupied orbital of a molecule and has, well, in like this case, reduced this molecule. Okay, so like this way, we can now think about a metal nanoparticle not only as a way to generate a hotspot of field around the metal nanoparticle, but also to generate a hotspot for our chemistry, for example. Yeah, and at our chair here, like in Munich, there's the group of Professor Emiliano Cortés, who has really looked a lot in the last couple of years, also first with me at Imperial College London, on how we can use these plasmons to locally control chemistry. Yeah, so I will show you now. Let me just skip those few slides here. Some examples, and actually I will also let me like skip this. I want to make sure we have a lot of time for discussion at the end. Let me maybe just like show you one really neat like example for like what you can like use this here. Okay, and like this is for some very clever, or like what we think some very clever self-assembly. Okay, for bringing structures close to a metal nanoparticle. I will like show you what I mean by this in like a moment. So suppose we have some metal nanoparticles, let's say 3 here, and we coat all of them with molecules. Okay, and now we excite a plasmon only in one of these particles. Okay, so like in like this arrangement that you see here, we can simply do that, for example, by illuminating with a polarization so that the plasmon only gets excited here. What will happen, and like we have shown this also now like almost like 3 years back, that if we excite a plasmon in here, and if the plasmon decays into such electron hole pairs, the electrons are actually able to cleave the bonds with which these molecules here are attached to the gold. These are so-called thiol bonds of this particle. So if we excite a plasmon, what will happen is these molecules will leave, and they will not leave due to the fact that we have an enhanced field, but we've actually shown that they really leave because the hot electrons get into these bonds and basically like cleave them off. Okay, and like the way like that this like actually works is, so they lower the thermal activation barrier for the cleavage operation, if you wish. Yeah. So now what you can do is you can now use this for like a clever like self-assembly, and like that's done in like the following way. So like let me first show you like that this actually works. So we take our 3 gold bars here, okay, and we coat them very like tightly, so with like a monolayer of molecules, and like what we use are these like thiol bonds, and we have little strands of DNA in it. Okay, and then we put a drop of solution on it with dye molecules, and these dye molecules have a DNA strand on them that is now almost complementary to this docking strand. And the almost is the important part, because that means that they will bind to the docking strand, they will feel the enhanced field of the plasmon, and due to the field enhancement, we get a flash of fluorescence. Okay, but then that binding breaks down because we don't have complete complementarity between these 2 DNA strands, and our molecule at that position basically goes dark again. Well, it leaves. So if we now collect enough flashes of light, we can run a so-called super localization algorithm in order to narrow down the point spread function of where that emission has occurred. And this allows us to take a super resolution fluorescent image, as you see below here, of the fluorescence of this particle. Yeah, so like with a resolution that's below the diffraction limit of light. Yeah, this is a similar principle, for example, that gets also used in stimulated emission depletion microscopy, where you use another technique to deterministically switch off fluorescence in microscopy that some of you might know got the Nobel Prize for Stefan for chemistry now also many years ago. But to cut a long story short, this technique enables us then to directly image the fluorescence here. Yeah? So you see a nice fluorescent image here due to these red molecules on our 3 gold bars. Now we excite a plasmon in it, in like this bar here on the left, just as in my animation before, these red molecules get cleaved off. So now you see, if you do the imaging experiment now, this bar went dark, and only this bar, because the fluorescent molecule, well, the like docking strands are gone here. Yeah? Our fluorescent molecules cannot bind to them anymore. The particle is dark. But what we can now do is, since we now have a bare gold surface here again, we can now functionalize this part here with another set of molecules, let's say with a green molecule. And this way, yeah, we have now selectively functionalized one particle here compared to the other 2. Yeah. So you may ask, oh, Okay, so like what's so like interesting about this? So what's interesting about this is that you can now use this, for example, for like nano fabrication, because what you can do now, for example, is you like do like exactly the same, but on your bare particle, you can now, for example, put a receptor that will then bind to a colloidal particle. Okay, so if you put, for example, biotin then on this bare gold surface, and in solution you have gold particles that are functionalized with a molecule called streptavidin. Streptavidin strongly binds to biotin, and this way we can bring gold particles to the particle of this 3-bar nano antenna that we like want to. You see some images here. Yeah, if we polarize in this direction here, we have cleaved off the molecules of this particle, so we were able to functionalize this with biotin. Our little gold bars stick only to this particle. Yeah. If we polarize in the opposite direction here, we affect these two particles. Our colloids stick to these particles. If we go in the direction just of this one, yeah, they mainly stick to that one. Yeah. So you see the like gist. And this is quite interesting because this allows us now to combine top-down nanofabrication, so lithography, which we have used to generate these nano antennas here. And yeah, thanks for that. And bottom-up self-assembly, since we were able now to bring these small gold particles to like wherever we like want. And so you might say, okay, why is this so like interesting? These are just gold particles. Well, they are just gold colors here because we can easily image them in like an SEM. But one straightforward way, like I had here, is now to do this with quantum dots, right? So this way you could, for example, if you want to make a small single photon emitter cavity, you could use such a technique to bring your quantum dot, to like a certain position in a metallic cavity. And you can then use also the same principle then, for example, also for purification and sorting. So if you have a little vial where you have two population of particles, let's say some rods and some spheres, and they have two different plasmon resonances, yeah, that are distinctly apart, so you can excite them either in the one or like in the other. Yeah, and if like they are now stabilized via their like surface groups, you can use this principle to cleave off the surface groups only of one population here, and then that population will then basically collapse, and you can centrifuge it out. Yeah, and then lastly, so for those of you that maybe have already looked a little bit into topics in nanophotonics, you can use this imaging, this like straightforward imaging recipe here that I've shown you now to actually also determine where has absorption occurred in such a small metal nanostructure, right? Because absorption has occurred, well, in the part that goes dark, because that's where you have excited the plasmon. Yeah, so if you have a more complex metal nanostructure where you can also have near field energy transfer, then you can this way find out in like which part of my metal nanostructure has actually absorption occurred. So the structure that we see here now, I will not go like into the details, but you see it is basically two disks. These disks interact strongly with light. They have a very strong dipole resonance. So they are the light harvesters, okay? And if we now put a little rod next to it, if we tune the like length of this rod the right way, we can be in like a situation where a resonance that on its own we couldn't excite in the rod, like a so-called dark resonance, that's a resonance that doesn't have a dipole moment, can couple to the dipole resonance in these disks. And like this way we can have a near field energy transfer. And then depending on the wavelength, we can switch this near field energy transfer on and off. So we can have one situation where our decay actually occurs in the disks, and we can have one situation where our decay, our absorption, occurs actually in the rod. Yeah, this is a so-called phano-resonant energy transfer. And with this super resolution imaging regime, you can now directly see that, right? So you see here the like disk goes dark. That's because the absorption occurred in these disks. Here the rod goes dark. That's because the absorption occurred in the rod. Okay, so I realized this was quite dense, but I hope I have given you a bit of a flavor about some like modern topics in nanophotonics with metal nanoparticles. Now, in my last few minutes, I wanted to talk a little bit more about metasurface holography, but I think I rather probably break now for the questions, and then if there's still some of you interested in that, I can just show a couple of slides for that maybe after the question time. So let me then just finish by highlighting that, of course, this work is all due to the PhD students, collaborators, and postdocs in my group, and I particularly for the work that I've shown want to highlight the group of Andrea Bragas at the University of Buenos Aires, with whom we did all of the phonon, the mechanical work that I've shown, Emiliano Cortés for the chemistry, also Sebastian Schlücker for the chemistry work. So let's have a question and answer session now, and then if there's a bit more time and some of you are interested in it, I can show you a bit more about holography for maybe 5 minutes. So thank you very much.
Okay, Professor Maier, thank you very much for your very nice and rich presentation. I personally enjoyed that, and I have personally a lot of questions. I would like to kick all of the participants out just to sit here and talk to you, but because of our limited time, we will pass some of the questions that passed here in the chat sections. Yeah. Professor Hafar always is asking that, do you do any numerical simulation to determine the best geometric shape of the antennas as a plasmonic platform?
Yes, sure. So like everything that I have shown here. So let me maybe go like just like back to one particular picture. Actually, I want to go back, sorry, since I can use this also to highlight a particular issue. And I want to go back to, sorry, this one here, where we see these modes here of these particles. Yes, so everything starts always with full field, and like we mainly use brute force, the electromagnetic simulations, so either finite difference time domain simulations or finite element modeling, so Maxwell's equations on a grid to determine where these plasmon resonances are. Since for the sizes here everything is classical, all you need to really do is having like a good like Maxwell solver. So you can get some intuition from analytics. So disks, for example, you can start with analytical formula from so-called me theory for a sphere. And then you can calculate where the plasmon resonances are. Yeah? So the only issue is that if you excite in the far field, yeah, and also if you excite in like with like an optical microscope, right? Obviously, you will only get the plasmon resonances that actually couple to the far field. So those that have a dipole moment, yeah, these are the ones that give, the like color to your metal nanoparticle. But there are also, of course, and I just very briefly mentioned this here, there are also modes that are dark, right? Modes that don't have a dipole moment. For example, the like simplest case, you have two particles, you can set the cloud via a plane wave, both into symmetric motion, so in the left particle and in the right when you move in phase. But of course, the other solution, right? If you just think about two coupled mechanical oscillator systems, so two masses on a spring, another spring in the middle is like an anti-symmetric motion. That mode exists as well. And that's actually the power of this technique. That's why I wanted to go back to this slide. Since of course, with like an electron beam, you can excite also these dark modes. And in a computer simulation, you can then also excite these dark modes if you excite plasmons not with a plane wave in your computer simulation, but with like a local dipole, right? So like that's what we very like often do. So this basically, just think of it, it kind of acts as like kind of like a delta function with which you excite your partial differential equation system, and this way you get out all of the non-transient solutions there. Sorry, all of the transient solutions there. Yeah, right. So we do a lot of computer simulations.
Great, thank you very much. Professor Albert also is asking, he first of all send his congratulations for that excellent presentation. He's saying that in our physics engineering program, we worked with plasmonic particles mainly in colloidal solutions, but we can synthesize plasmonic molecules, dimers, and trimers. is it possible to perform the detection applications shown in nano antennas in a colloidal medium?
Yes, I mean, so the strength of the colloidal medium is, of course, that you have superb materials, right? The big disadvantage with this top-down lithographic method here is that usually we have polycrystalline materials, right? Since our lithography is followed by via either an evaporation or a sputtering process, right? You can see this here in this high resolution TEM. The big advantage, of course, of lithography is that it allows us to really control the size and the distance. Yeah, that is also possible in colloidal form to some extent. If you think about self-assembly techniques such as DNA origami. Yeah, so the physics that I've shown here, everything is also possible in colloidal form. Yeah. That's why we are actually, so just as a side again, that's why we are also so interested in, I'm not going to go back to that slide now, it will take too much time, in this process via this hot electron induced cleaving, right, that we can use to kind of marry these two worlds, right? So we can make metal nanoparticles with lithography, but then put colloidal particles, with a certain accuracy, of course, to where we want it. But yes, so I think the field of colloidal plasmonics is probably at least, if not bigger. So in sensing, for example, it's bigger than the field with a top down.
Thank you very much. Mariana also congratulates the presentation. She's asking, what is the efficiency obtained in the energy transfer by using the nano transducers?
Yeah, that is an absolutely excellent question, and and the answer is we don't really know. It's very low, right? Because I mean if you just look at this picture here again, so most of the energy actually goes into heat, right? It goes into disorganized motion of atoms in these particles. Yeah, so actually one of the applications of plasmonics is actually also as localized heat sources. Yeah, so there's a large program mainly in a cancer center in Houston where actually plasmon modes, again in colloids, since we just spoke about colloids, get actually used to locally increase the temperature in cancer tissue. Yeah, so this what they do is basically they functionalize their metal nanoparticles so that it mainly binds to cancer cells. They choose the size of these particles so that the resonance is in the near infrared where the body is transparent, and then they illuminate with near infrared light at plasmon resonance, and the particle heats up just by a few degrees, usually 5 or 6 degrees. It heats up the cells surrounding it, and this very gentle heating is then enough to induce spontaneous cell death. So most of the energy goes into this heat. Now, what amount of energy goes into the actual mechanical displacement, so into the coherent excitation? That is I can't answer that. It's going to be a very small fraction. So from these experiments here that I've shown here, we can kind of estimate a little bit by basically, taking a look that if we pump one particle here, right, and then we probe here, this way we can kind of make best guess estimates, how much energy do we lose here, how much here, and how much here. But it's at least, I would say, maybe 10 to the -5 or so efficiency. But yeah, so I'm not aware of any particular study that has actually looked into that. Yeah, it would be something very interesting to actually determine. And you could potentially think, what if you would put your particle now actually on a piezoelectric substrate, right? Could you then maybe via a voltage readout actually answer the question that you just posed? Yeah, but it's very low. Yeah, so the power is that it's local though, right? So that's the point, right? You can excite it in a very small area, and the frequency is very fast. It's in gigahertz, but the efficiency is very low.
But let me complete this question. Does it energy transfer rate depends on the morphology of the nanoparticle?
Yes. So if you talk here about the acoustic energy transfer, it like actually depends not only on the morphology on the particle, but it also depends very much on the like interface between the particle and the like substrate. So, you know, if you choose a different adhesion layer, for example, often like gold doesn't stick very well on like glass, right? So you might want to put a chrome layer in it, just a couple of nanometers, or like a titanium layer, and that changes these frequencies quite a bit, and also the efficiency of like excitation. You can think about it just as an optics. You can think about it as an impedance mismatch problem, but now just kind of like an acoustic impedance mismatch.
Okay, Professor Stefan Maier, just let me ask you one very simple question that a undergraduate student could answer, could ask. That he may ask, Professor, I know that what is an atom and what is a molecule and what is a polymer, what is a bulk material. But when you go to the talking about a nanoparticle of 20 nanometers, how is the arrangement of the atoms? How is the arrangement in this volume?
Well, so for the materials that we deal with, and for the processes where we like excite these plasmons, when you do the like modeling there, you can basically model the particles. So basically the like lattice that the particle is on completely as like if it would be a bulk, simply because you have so many free conduction electrons available, right? Like we have a density here of 10 to the 23 per cubic centimeters, that like for the motion of this electron cloud, you can think about the particle as a bulk. That like being said, many of the most interesting processes, particularly these processes that are hinted at the end on chemistry and then on charge in injection from a decaying plasmon into a molecule, that of course depends then very much on the surface of your particle, you know, and there the arrangement of the atoms can now like vastly like differ. So then it really depends how the particle is made, right? So like I think it was Albert that asked, like, what about colloids, right? So like if you have a colloidal particle, right, then you very often have a very distinct arrangements of the atoms on the like surface, right? Some like sort of preferential crystal orientation. If you make our particles in the more brute force way, let me again try to find a good SEM picture here, right? Then nothing is unfortunately as nice. So you don't have a really nice surface, clear like surface reconstruction as you would have in like a colloid, right? Because you have like a very like, you know, poly like crystalline system with a lot of dislocations, you know, missing like atoms. Yeah, but like from a first like approximation for the like optical modes that you excite for the plasma modes, that doesn't really matter. That becomes important when you look at the charge transfer process, but not so much for the process of the light, of like where the light modes are. That like being said, if you have a very rough surface, then actually these field hotspots here can be even higher than if they would be on a smooth surface. And that's very similar to like the lighting rod effect that you know from your like textbook, right? If you think about an electrostatic case and you have a very sharp corner, yeah, then you have a crowding of the electric field lines, right? If you want to protect a building, right, from like lightning from the like atmosphere, right? You like have a metal rod that you point up, and then that's where the lightning hopefully strikes, right? And like that is like very like similar here as like, well, like if you have a very rough surface, you get a crowding of the electric field lines, and these field hotspots here can become even hotter, meaning they can be even larger field enhancement than when you have a very smooth surface.
Okay. Thank you very much again, Professor Stefan Maier, for your nice presentation and accepting our invitation. I hope that in another opportunities we can have you here in Brazil. And
yeah, it would be very nice. I was in Recife not many years ago, actually. I think 4 years ago or so. Enjoyed it a lot. So it would be nice to come back.
Thank you very much and have a good time.
Yeah, thank you very much as well. And have a good rest of the day. I think you have your closing ceremony now. So enjoy.
Exactly.
So I will stop sharing. Yeah, thanks again very much for the invitation.
Thank you very much.